So today I'm going to do a latent growth curve model in R. We're going to start with the most restrictive model and work to the least restrictive. So it's going to get more complex as we go. We should see improvement in fit to the data set as we go through the models. And so here we go. I am actually looking at commitment scores. They've been measured at 4 time points, year 1, year 2, year 3, year 4. For my employees in my organization, there are 952 employees who filled out the measure at each of the 4 time points, so I have no missing data. And I'm just looking to see if there's any trajectories within my data set as far as commitment scores go over time and the role that time plays in the commitment scores. So I'm first going to install and library my packages. And then I actually, instead of inputting a data set, I went ahead and inputted the covariance table and the mean scores for each point. You must put in the mean scores for each point to be able to run a Lgcm. So next I'm going to run the first model. It's an intercept-only model and it has no slope. I want this model to have bad results because otherwise I'm saying that one average score is the best score for all of my time points, and we actually want to see change within this data set. So my intercept variance is constrained to 0, right here. It's constrained to 0, so that can only get a mean. My residuals are forced to be the same for each time point, as you can see right here. And so that's saying that variance is the same across all the time points, which may or may not be true due to sphericity, but since I'm starting with the most restrictive model, that's the way I do it. I'm including an intercept latent that predicts the time points with each path set to 0, which is right here. And this forces all the estimation to occur at the means level of the latent variable, and then I'm turning off right here in this line. I'm turning off the intercept variance. So, and then right here, as I said, is actually where I'm setting the residual variances to be the same. So they're equal by taking average of all the residuals. And what this is doing is just my first model. And I will go back and say that right here, this is where you're naming each time point within the data set. And so each row represents a time point and column is a covariance table at a time point, and that's just this right here. And we wouldn't have to do that if we had input our data correctly, or not correctly, but from a normal data set. So I am actually going to create the parameters for my model that I just explained, and here's where I'm actually going to run the model, and it's using the, oh goodness, I gotta do this first. There we go. Now we do this. And it's using the model I just created, the covariance table that I created at the very beginning, the mean table created at the very beginning, and this is how many people are my sample, which is 952. So that we've run the model, we're going to look at the descriptive statistics. And let me pull this up so you can see a little more. So my chi-square is right here. This is degrees of freedom. It's significant, which is typical when running SEM models. You don't really pay as much attention to those. I would like to say that when I ran this model, I used the growth command, which operates in a similar manner to the CFA or SEM functions. So this summary doesn't tell me much in terms of the fit statistics, but it does show that my regression coefficients have been set to 1, and that I don't have any intercepts since I forced them to be nothing right here. And I do see that my I-intercept right here, which is the mean of the score across time points, is equal to 5.352. And the residual variance across the time points right here is 0.636. So overall, I'm going to run these fit statistics to see if it's a good model. We don't want it to be once again. So this is where we're running the fit statistics. And it gets my parameter estimates with confidence intervals and then my fit indices. And so we're going to run that right here, which is the fit indices. And what you can see from this is that my RMC is a 0.551 And then my, it's kind of difficult to see within here, but here's my chi-square again, my degrees of freedom, my p-value, here's my Ramsey, right here is 0.550. We're also going to look at the CFI and the SMRM. MR right here, this one's important, and the CFI, which I current right here, 0.000. So this means that my model is a very bad model. CFA is very low, Ramsey's low, but we wanted this because we wanted to expect time to affect change and for change to happen over time. So now we're going to move on to model 2 since that one did not fit our data well, and we're going to run it. And this model, we still have an intercept-only model, but we allow the variances to be greater than 0. Therefore, it's a random intercept model, meaning that people start in different places. So at the intercept. So some people start a little higher at time 1, and others start a little lower at time 1 on their commitment scores, which seems realistic. And then if we find that the variance here is really small, then it implies that everyone is starting in the same place. So we hope that that doesn't happen. And then we also force the residual variances to be the same and do not include a slope. So here the residual variance is the same. We don't have a slope. Here's the intercept as well from what I just explained. Here we're actually going to run the model. It's the same code as before, just changing the model to the new one. Then we're going to look at the descriptives. So for this one, chi-square is 555.313, 11 degrees of freedom. It's significant. The I changes slightly to 5.352, which is right here, so that's the intercept. Within all the models as we go, we want them to improve and fit, and we want the residuals to drop. The residual went from model 1 of 0.64 to 0.16 in this one. The mean is 5.35. And so people are varying about half a point. Intercept variance is 0.48. And so now we're going to run the others to get these others. So here's the parameters. And as you can see, it's a little difficult, but it does have the confidence intervals, which is important. And now we're going to do the fit measures, which really helps us to look at things. So once again, we're looking at, here's a chi-square degrees of freedom p-value. We're interested in the Ramsey, which is 0.228. We're also interested in SRMR, 0.092, and the CFI, which is 0.838. Which is an increase from the last model. So therefore this model is better, and I'm going to keep going to try to obtain an even better fit. Any CFI change above 0.01 tells me that I should keep going. So for my third model, I'm actually going to add in this slope component, but a random slope. A random slope isn't necessarily good because it implies that everyone would be changing in different ways, and we would prefer for everyone to change in the same way, so systematically. So we want for them to change over time, but not randomly. We want the time to actually be the reason that they're changing. So we start with the random slope to see if it's better than no slope at all, and we estimate, and then we're going to estimate the real slope in hopes of an even better model. So for model 3, here we are, and we're actually going to set the slope to 0, but we still allow the slope variance to exist. We uncorrelate the slope and the intercept. We leave the intercept in its variance in the model. We add the slope but turn off most of its components. So overall, model 3 has intercept lines, slope latent, slope mean set to 0, covariance between the slope and the intercept at 0, and residuals estimated to be the same each time, as we've done before. Now, one thing we have added is that we do have a slope for the latent variable now. The regression coefficients are still set. Covariance between intercept and slope is still 0 like before. And the intercept, which is basically the mean for the slope, is 0. So we're estimating that no slope occurs at the moment. So when we run it, first creating the parameters, now we're running it. Now we're going to look at the descriptives. So when we run it, we find that the average intercept is 5.26, which dropped a little since the last model. And the residual variances also dropped, which is good. So we're looking right here and right here. And that's a good thing. We want those to keep dropping. There is a bit of variance around the 0 slope. So you're essentially saying that slope is flat, but then estimating that some people might be flat on that flat slope, but others might not be. They might be around it. There's variance in terms of the slope for each person. And so now we're going to look at the others. We're going to look at the parameters and the fit measures. And so we see that the intercept mean dropped just a touch, the intercept variance stayed the same, the residual variance dropped, and the slope variance is about 0.03. When we look at the CFI, it changed from 0.838 to 0.902, which is approaching a good range, and it's a significant change in the positive direction that's greater than 0.01. So we keep going. We go to the next model. And also when we look at the RMSE and the SRMR, they're still not acceptable yet. So the SRMR is 0.149, which is not acceptable, and RMSE is 0.186. So for our fourth model, which we're about to run, we're going to take out the covariance. So we're going to allow our slope and intercept to vary. We also include a real slope, and so we're wanting this model to be the best because it's an actual estimation of the slope within our data set. The point of the latent growth model is to show that things are growing or decreasing and that there's a significant change, a significant slope. So we go ahead and create it. Those are the parameters, and here we're running it. And then here's the descriptive statistics, as you can see. And so what we find is that the average intercept is 5.26. Excuse me. The average intercept is 5.183. But we find that when we look at these, our intercept dropped just a little bit to 0.113 right here, which is significant and good. The variance dropped a little bit, and the spread around the intercept increased just a touch to match the increase in the overall average. The variance for the slope dropped, and it's a significant variance around the 0.01, but it's a very small amount of change from the actual slope. The residual variance is what we're looking to change in each model, and since our slope is not too large and the variance around the slope is not large, that implies that there's not a lot of interaction going on between the different slopes in different directions, which is good. If we have a slope of about 0 and a very large variance, then we need to investigate why that's happening. There's some reason. And the covariance is the trickiest thing to interpret, and we'll look at it. It is actually a negative 0.02. And the negative 0.02 means that there's a negative covariance. So people are starting at high points and they're correlated with low slopes. So since the slope is positive, this means that people who are starting with a higher score on commitment at time 1, their commitment scores are increasing slower over time than people who start with commitment scores lower. Those are increasing faster over time. So a significant change in the model fit from 0.902 to 0.995 for the CFI indicates that this is a very good model. So when we look at the fit statistics overall, the CFI, the SR, MR, and the RMSE, they're all very good. So this model is probably not going to get any better, but we tested a totally unconstrained model just to make sure that we cannot get any better fit. So when we go to model 5 right here, which I'll go ahead and set the parameters before I talk about them, we're taking out the residual that's forcing the residuals to be equal, and we're instead allowing them to vary. So if the residuals vary at the different time points, this implies that there's bigger error at some time points than others, which would be a sphericity issue. We also want this model to not be significantly better than the previous models because we want the residuals to be small and roughly equal. But by taking out the parameters for the residuals and only leaving the intercept and slope lines, we're able to make sure that our model is actually the best fit for our data. So now we're going to run it. And it's just the same as before. We're just changing the model again. Now we're going to look at summary and then the parameters and the fit measures. So the summary shows that the coefficients are still not changing. If we go back up here, the coefficients are still set, and this is each time point. So they're still not changing. The covariance, intercept, and slope are all about the same. The variance go from being 0.11 for all of them to changing. So right here, they're all different because we're letting them be different. We then run the fit indices, which I've already run, but here we go. Here's parameter estimates. Here's the fit indices. And this is just allowing us to look further into the variance changes to make sure that this model is not significantly better than the other one. So pretty much what we see is nothing's changed. The model is not significantly better than the previous model. When we have models that are both really good and approximately the same, we typically go with the simpler model, which would be model 4, because it has more constraints than model 5. The reason that it is more constrained is because the variants are constrained to one number instead of allowing for 4 at each time point. And so since 4 is the best in terms of results and changes from the previous models, as well as being the simplest, we decide that model 4 is the best fit for our data. So if we kind of step back and we think about what we've just figured out about our data set, we found a model with random intercepts, which is good, meaning that the people started at different places around the average starting point. So that was time 1 for commitment. We also found a model with a slope, which is good because it implies that there's change or growth over time. Our random slope is not significantly better, so that's great. It says that model 4 is better than model 3, which implies that people are changing approximately the same across the time points in the same way and direction, so systematic change. There's also significant covariance, and it's negative covariance with a positive slope, which means that people within our data set, if they start high on a commitment score at time 1, their score goes up much slower than people who start lower on commitment score at time 1, and theirs go faster. So overall, model 4 is the best fit for our data. We compare each model successively, and each model releases a component allowing for more complexity. And we always go with the simpler model that still fits the data well. And we found that model 4 estimated that growth happened, but it wasn't random growth. It was systematic growth within our data set, so systematic change. And the errors are approximately the same for each time point, which is good.